There's this fear or discomfort that some individuals feel when they encounter clusters of small holes, bumps, or irregular patterns on a surface. This could include things like the texture of honeycombs, the pattern of pores on certain objects, or the look of some natural formations like lotus seed pods. The anxiety caused by these dense hole-like clusters stems from the brain's tendency to find these patterns unsettling, and it can provoke feelings of nausea, disgust, or an overwhelming sense of unease. This response is often due to the unusual and unnatural look of these patterns, which seem to defy the typical order we expect in nature, and can invoke an instinctive reaction to discomfort. This kind of fear has been formally identified and studied under the term Trypophobia. It's not a universally recognized disorder, but it's a phenomenon that's commonly reported by many individuals with varying degrees of severity. This same fear can extend to cosmic contexts, like the look of small and dark regions in space, especially black holes. Just as clusters of holes on a surface seem unnatural or unnerving, the idea of small, isolated black holes scattered throughout space might evoke the same unsettling feelings. These black holes, with their absolute darkness and emptiness they represent, might be subconsciously seen as holes in space itself, and it can trigger the same primal fear. After millions of years, a star at least 20 times the mass of the Sun has reached the end of its life. It's exhausted the hydrogen in its core and runs out of fuel to burn. There's no more nuclear reactions to counteract gravity within its core. The core starts to collapse under its own weight. Gravity begins to take over. If the core's mass exceeds about 3 solar masses, no known force can stop the collapse. The star swells into a red supergiant, its outer layers expanding outward and violently ejected in a supernova explosion. An event so bright that outshines the entire galaxy. But that's not the end. The core of the star continues to collapse, becoming denser and denser. As it shrinks, gravity increases, pulling everything inward with an irresistible force. There's no longer a star, but a collapsing core of unimaginable density. The collapse continues until the core reaches a point where not even the strongest forces of nature can stop it. The core is crushed into a singularity, a point where space-time curves infinitely. A black hole is born. Anything in the universe, if compressed to a small enough size, its escape velocity exceeds the speed of light, meaning nothing can escape its hellish gravitational pull, and turns into a black hole. If Earth is compressed into a sphere with a radius of 9 millimeters, it would be physically impossible to overcome its escape velocity, and will turn into a black hole. Compressing an object to these extreme sizes requires unimaginable energy far beyond our current capabilities. Such implosions take place across the universe within the course of massive stars towards the end of their lives. Stars that are at least 20 to 25 times the mass of the Sun. Every time you look at a black hole, in a sense, you're most likely looking at a massive star's corpse. The more massive the core of the star, the greater the force of gravity would be to compress the material inside star's core, and more likely would lead to the birth of a stellar mass type of black hole. A typical stellar mass black hole is as massive as 3 to 100 suns. It takes millions up to billions of years for a star to die and turn into a black hole. At the same time, the universe is ginormous, and rare events happen all the time, which is why it's filled with stellar mass black holes. One study investigated the demographics of stellar mass black holes and tried to estimate their population in the whole universe. The study concludes that as of now, there are 40 times 10 to the power of 18 black holes within the observable universe. The observable universe is a sphere around 93 billion light-years of diameter. Within this sphere, there are 40 billion black holes, 4 followed by 19 zeros. The investigation revolves around the number of black holes in the universe and various formation channels for black holes of different masses, like isolated stars, binary systems, and stellar clusters. Calculations show that about 1% of the baryonic matter, meaning ordinary or normal matter composed of protons and neutrons in the universe, is trapped in stellar mass black holes. Black holes are completely invisible when not actively interacting with their surroundings. Their gravitational pull is so strong that not even light can escape from within their event horizon. This makes them completely dark in isolation. An inactive black hole drifts silently through space, giving no visual indication of its presence. No glowing accretion disk. No energetic jets, just a void. The detection of these sleeping black holes depends on indirect methods, observing their gravitational influence on nearby stars, or detecting disruptions in cosmic gas and dust. This invisible nature of a black hole taps into the primal fear of the unseen and uncontrollable. Just like how frightening the ocean depths are with their hidden dangers, deep space hides silent predators like resting black holes. This is a unique, enormous, very sharp and detailed space map. It looks like a nice and calm starry night, but there's nothing calm about this image. This is a collection of 25,000 active supermassive black holes, located in distant galaxies. Each of these supermassive black holes are swallowing dust and gas at the center of their host galaxies, releasing enough radiation for us to detect. Black holes are natural consequence of universe's processes, primarily forming from collapse of massive stars. The huge number of stars in our Milky Way galaxy, estimated at around 100 to 400 billion, shows that black holes are not rare phenomena, but rather a common part of the galactic ecosystem. While not every star becomes a black hole, the widespread presence of massive stars, combined with billions of years of stellar evolution, suggests that millions, up to billions of black holes have already formed in our galaxy over its 13.6 billion years or so history. Stellar mass black holes formed from the collapse of massive stars, estimated in the tens of millions in our galaxy alone. Intermediate mass black holes are thought to exist in star clusters and other dense regions, likely formed through mergers of smaller black holes or direct collapses in early star-forming regions. Numbers are harder to estimate, but evidence points to thousands or more scattered across the galaxy. A supermassive black hole, Sagittarius A star, lives at the very heart of the Milky Way, in the dense region known as galactic center, approximately 27,000 light-years from Earth, weighs about 4 million solar masses. While the galaxy's large-scale gravitational forces are dominated by dark matter, the central black hole serves as the anchor for the dense inner regions, making it pivotal to the galaxy's rotational symmetry. This is an object so extreme that has dominant gravitational influence in the inner few light years of the Milky Way galaxy, tens of millions of solar masses. The event horizon of black holes is the limit, a boundary for our understanding of the universe. The edges of these extreme space-time regions are where human knowledge comes to a halt. At the heart of a black hole, at the very center, lies the core of the Death Star, reduced to a single infinitesimally small point. Assuming it's not a spinning black hole, the entire object has crushed into a single point, the singularity that hides its secrets from the rest of the universe. This point, where the core of the star has collapsed and space-time curvature becomes mathematically infinite, is always hidden behind event horizons. They're inherently beyond observation. This censorship prevents the extreme and incomprehensible nature of singularities from influencing the external universe directly. The event horizon is also the boundary that marks the point of no return around the black hole. Once anything, any kind of matter or light, crosses this region, it can't escape the black hole's extreme gravity. This is why we can't directly observe what happens on the other side. Once something crosses the event horizon, it gets causally disconnected from the rest of the universe. The extreme curvature of space-time in this region renders any interaction with the outside universe impossible. Events that happen inside the event horizon can't influence anything outside of it. The normal flow of cause and effect is disrupted, creating a region where information is effectively lost to the universe. This is a fundamental breakdown in how we think about causality, as it suggests that there are parts of the universe where no future events can affect the outside world and vice versa. If you were to fall into a black hole, you would be completely isolated from the rest of the universe. You wouldn't be able to communicate with anyone. While you're still alive, any hope of rescue would be utterly hopeless. That's the ultimate form of loneliness and isolation in the universe. It's the fear of being utterly disconnected from the rest of existence, unable to reach out to anyone or anything, trapped in a timeless, incomprehensible void. Any traveler approaching the event horizon, from an observer's perspective, watching the traveler approaching the black hole, would appear to slow down as they get closer to the point of no return and eventually freeze in time. This is due to the immense warping of not just space, but also time, since space and time are inseparable and form the same fabric. The traveler itself experiences something different. It continues to fall into the black hole without noticing anything unusual. Once it crosses the event horizon, it's cut off from the rest of the universe. There's no way for any signal, information, or even causal influence, like light or gravity, to travel back to the outside universe. The region beyond the event horizon is causally isolated from everything else. Black hole's gravitational force dominates the surrounding space, while the universe outside remains unaware of the mysteries locked inside. Inside the black hole, passing its event horizon is where things get very strange. The laws of physics here are no longer what they were outside. The singularity becomes the inevitable destination. There's no way to turn around, no way to stop or escape. Gravity becomes infinite, and space-time is bent beyond recognition. The only direction available is toward the singularity at the center. a place where gravity crushes everything to an infinite density. Space-time loses all meaning, and the known laws of physics break down. All paths, all directions, and all time converge toward this one point at the very center. Anything that falls in is doomed to disappear beyond the event horizon, trapped forever in the black hole's grasp, cut off from everything outside. The roles of time and space inside the event horizon are reversed. The direction pointing toward the singularity becomes like time, meaning it becomes inevitable. Once you cross the event horizon, it's impossible to stop your fall towards the singularity. Just like how we can't stop the passage of time, the singularity lies in the future in the sense that you're drawn towards it, and no force can reverse that motion. Nothing can escape this pull, because the space-time curvature is so severe that the directions bend toward the center. There are no escape routes. Moving towards the center, the gravitational pull increases exponentially. Approaching the event horizon, the difference in gravitational forces between the top and bottom parts of the body becomes incredibly large. These differential forces stretches the traveler's body vertically, pulling apart along the direction of the gravitational gradient. Essentially, this results in the body being pulled into a long, thin shape, like a strand of spaghetti, which is why it's called spaghettification. While the stretching occurs along the vertical axis, there's also a compressing effect along the horizontal axis, or sideways. This happens because the tidal forces are so extreme that they also squeeze the body horizontally as they stretch it vertically. The traveler is stretched into a long, thin noodle while being squeezed in perpendicular direction. The closer to the singularity, the stronger the tidal forces become. All forces intensify, and compression grows increasingly violent. Eventually, the extreme forces would rip apart the traveler's body, atom by atom. The process would continue until all matter was broken down into its fundamental components. Eventually, every single elementary particle, what's remaining of the traveler, would be crushed into the singularity, where all the laws of physics as we understand them break down. The human body, fragile and susceptible to extreme forces, becomes a central symbol of vulnerability. How small and defenseless we are in the context of the cosmos. And spaghettification is the most extreme and visceral representation of cosmophobia. More specifically, the fear that space can expose inherent weakness and mortality of a human body. Spaghettification is a vivid and graphic representation of how strange and horrifying the universe can be. The notion that universe can be so alien and hostile to human life that it could rip you apart on an atomic level is both a terrifying thought and depiction of the violent, brutal, and unfathomable power hidden in space. The inescapable fate after falling into a black hole, the very idea of being helpless as your body is stretched and torn apart by gravitational forces that exceed anything experienced on Earth, plays directly into this fear of helplessness and the loss of agency. The concept of being stretched and compressed to the point of annihilation is a psychological horror. Your body is ripped apart as you approach the singularity. This type of destruction is far more terrifying than any ordinary death. Spaghettification, as a process that ultimately leads to the point where the universe's laws break down in extreme gravity, is also a manifestation of fearing infinity. The concept of falling into such an unknown, uncharted territory where normal rules of physics no longer apply is just terrifying. No matter what we do, the vastness of space and powerful forces within it are beyond our control. and spaghettification is a great example of this inevitability. Once you cross the event horizon, there's no escape, no possibility of survival. The forces at play are so overwhelming that your fate is sealed the moment you enter the black hole's gravitational influence. This speaks to the broader fear that we're dealing with forces we can't even fathom fighting against. In the final stages of spaghettification, the concept of time and space breaks down due to the immense gravitational forces. Anyone falling into a black hole would experience time in an increasingly unusual way, and at the singularity, time may cease to exist entirely. This warped perception and the loss of control over reality are powerful elements of fearing space. The idea that space can distort our perception to such an extreme degree results in the fear of losing our grip on reality. There's a direct correlation between the mass and the size of a black hole, or its event horizon. The more massive the black hole, the larger its event horizon will be. The mass of a black hole is expressed in solar mass. One solar mass equals the mass of our Sun, 4,384 billion pounds. Stellar mass black holes are 3 to 100 solar masses. Intermediate mass black holes, 100 up to 1 million solar masses. Supermassive black holes, located at the center of almost all galaxies in the universe, range from millions up to billions of solar masses, including the one at the center of our galaxy, as massive as 4 million solar masses. Ultramassive black holes range from 10 up to 100 billion solar masses. Two examples of ultramassive type, which have been the record holders as the most massive discovered black holes for many years. Hulberg 15A, located around 700 million light-years away from Earth, with allegedly 40 billion solar masses, and Ton 618, as massive as 40,700,000,000 suns. This black hole alone is more massive than all the stars in our Milky Way galaxy combined. Ton 618 is around 10,000 times more massive than Sagittarius A star, the supermassive black hole at the center of the Milky Way. The size of the event horizon of a black hole grows linearly with the mass. The radius of Ton 618 is around 390 billion kilometers in diameter. That's more than 86 times the size of Neptune's orbit. Theoretical models suggest that the maximum mass for a black hole is around 50 billion solar masses. Considering the age of the universe and the amount of matter available, there isn't enough time for black holes to go beyond this mass limit. Yet, the universe always finds a way to surprise us. The Phoenix Cluster is a gigantic galaxy cluster, located at a co-moving distance of 8.61 billion light-years from Earth, one of the most massive known clusters ever discovered, as massive as quadrillion solar masses. The Phoenix Cluster's exceptional characteristics have led to comprehensive studies, since it's a crucial object in its class. At the visible core of Galaxy Cluster lies Phoenix A, a luminous Type II Seyfert galaxy, ranked as one of the largest known galaxies ever discovered. It undergoes an intense starburst, marking the most significant star-forming event observed within any galaxy cluster. This galaxy is converting material into stars at a remarkable pace of 740 solar masses annually. To compare, the Milky Way's rate is 1 solar mass per year. Phoenix A has an active galactic core powered by a central supermassive black hole. This black hole has characteristics more extreme than any model representing the theoretical limitations of a black hole. Called Phoenix A star, or simply Phoenix A, this central black hole has an estimated mass of 100 billion suns, potentially even more than that. A black hole of this magnitude is 24,100 times more massive than the one at the core of the Milky Way, and has twice the mass of the Triangulum galaxy, including its dark matter halo. Triangulum galaxy is 61,100 light-years across, the third largest member of the local group of galaxies, behind the Andromeda galaxy and the Milky Way. If Phoenix A star is a non-spinning black hole, its huge event horizon would have a diameter of 590.5 billion kilometers, which is 100 times the distance from the Sun to Pluto. It'll take 71 days and 14 hours for light to travel the circumference of this black hole. Such immense mass potentially categorizes this black hole as one of the stupendously large black holes, a category of black holes with masses equal to or greater than 100 billion solar masses. The general thought about the formation of supermassive black holes at the center of galaxies is the merging of smaller black holes, consuming huge amounts of matter around them and eventually gain supermassive sizes. But this model just doesn't hold when it comes to the most massive black holes like Phoenix A star. Even the entire age of the universe isn't enough time for a black hole like this to gain its gigantic size. Hypothetically, stupendously large black holes can gain up to 1 quintillion solar masses. 1 quintillion is 1,000,000 times 1,000,000,000,000. A stupendously large black hole of 1 quintillion solar mass would have an event horizon of 620,000 light-years across. Space-time is a flexible fabric that can stretch, compress, and warp. Gravity works not as a force between masses, but as the warping or bending of space-time itself by objects with mass and energy. When massive objects like stars and planets move or accelerate, they create disturbances or ripples in this fabric, known as gravitational waves. Like when you throw a stone into a pond, creating ripples that spread out across the water. Similarly, when a massive object moves throughout space, it generates gravitational waves that grow outward through space at the speed of light, stretching and compressing space as they grow. These space-time ripples, traveling throughout space at the speed of light, become incredibly powerful when extremely massive events occur in the universe. The most powerful one is the merger of two black holes. When two black holes orbit each other, they gradually get closer and move in increasingly tighter spirals due to the gravitational attraction between them. As they accelerate, warping of space-time becomes more extreme, and the amount of energy radiated by this system in the form of gravitational waves increase dramatically. The environment around the system becomes an extreme zone of violence, destruction, and chaos. In the last stages of their orbit, the black hole's gravity warps the space around them, pulling in massive amounts of gas, dust, and even entire stars. This material is often accelerated to nearly the speed of light, forming accretion disks that can generate intense radiation. The space near the black holes becomes very unstable. As they get closer and their speed increases, the tidal forces exerted on nearby objects rip them apart, The frequency of gravitational waves increased dramatically as the black holes spiral closer. As these waves travel through space-time, they carry energy across huge distances. They stretch and compress the distances between objects, causing tiny vibrations in space itself. The merger itself is where things get truly terrifying. The energy release of the final merger is the most powerful event that can occur in the universe. While supernovae and gamma ray bursts are extraordinarily energetic, the merger of two black holes in a binary system dwarfs them in terms of raw energy. In the moments before black holes collide, the energy they release causes space-time to warp so intensely that they're detectable from Earth, even if they're millions, if not billions of light years away. The ripples sometimes travel across the majority of the observable universe. In fact, the energy released in these waves can be more than all the energy emitted by all the stars in the observable universe combined at that moment. The intense burst of energy produced during this merger is also the brightest form of energy release in the universe. While black holes themselves don't emit light, the events leading up to and following their merger, like matter acceleration, the generation of gravitational waves, and the production of high-energy radiation, can be incredibly bright and energetic. Even imagining such enormous forces could be cosmophobic. The idea that the universe is capable of producing events so violent, so powerful, and in many cases unpredictable, can trigger a deep existential fear. There's nothing we could do to stop these forces, nothing to shield ourselves from their effects, and no way to truly grasp the scale of destruction they can cause. The sheer scale and intensity of these events dwarf any human experience. The cosmic terror lies in the knowing that such events, while distant and unthreatening in the immediate sense, are happening on a scale that's both incomprehensible and totally unstoppable. Black hole merging is an incredibly rare occurrence. Two massive stars might form close enough to each other in a stellar nursery, or, over billions of years, two existing black holes might be drawn together by the mutual gravitational attraction of nearby stars or other cosmic phenomena. Even more rarely, these black holes would need to be in an orbit that brings them gradually closer until they eventually merge. The distances between stars and black holes are so enormous that the chances of two black holes happening to cross paths in a way that leads to a merger are very low. Even within a galaxy like the Milky Way, with hundreds of billions of stars, the likelihood that two black holes would come into close enough proximity to each other to eventually merge is an extreme cosmic rarity. The process of two black holes spiraling toward each other and eventually merging can take millions up to billions of years. The timing depends on the size of the black holes and their relative velocities. Even though black hole mergers happen far away from Earth, the fact that the universe is capable of generating such extreme events evokes a sense of vulnerability. The potential for a catastrophe in the distant future, one that we can't see, predict, or avoid, adds to this discomfort. The universe is vast and indifferent, filled with catastrophic events that we can't even hope to comprehend. They're totally beyond our influence, and our safety is completely irrelevant. There are galaxies, ginormous structures containing hundreds of billions of stars. Then there are galaxy groups, galaxy clusters, and superclusters. This is a galaxy cluster with two separate pairs of cavities. Now imagine how large those space holes could be. Galaxy clusters are the largest known gravitationally bound objects that have formed through the process of cosmic structure formation, containing hundreds up to thousands of galaxies, enormous amounts of hot gas and dark matter. The hot gas that dominates clusters contains much more mass than the galaxies themselves, and glows brightly in X-ray light that we're able to detect. This image shows two separate gigantic pairs of cavities that are extended away from the center of the galaxy cluster RBS 797, located around 3.9 billion light-years from Earth. The possible cause of this horrifying cosmic scene may have been related to eruptions from two supermassive black holes orbiting each other from a close distance. Galaxy clusters have one large abnormally bright galaxy at their center called the brightest cluster galaxy, or BCG. The captured eruptions must come from regions near a supermassive black hole in the middle of the massive BCG. Matter spreads away from the black hole as energy jets in opposing directions and blows cavities in the hot gas. The two black holes will continue spiraling each other and generate huge gravitational waves and ultimately merge. For several years, astronomers have observed unexplained gravitational anomalies in the outer reaches of our solar system. These anomalies suggest that something massive is exerting gravitational pull that can't be fully accounted for by the known planets. The gravitational pull seems too strong to be caused by any of the known planets, tempting scientists to consider the possibility of an undiscovered planet lurking in the far reaches of the solar system. This hypothetical planet would be far beyond the orbit of Neptune, possibly within the regions beyond Pluto, too distant and faint to be detected with current technology. The exact distance is unknown, but is speculated to be about 300 to 1,000 astronomical units from the Sun, where 1 astronomical unit is the average distance from the Earth to the Sun, around 93 million miles or 150 million kilometers. This object, often referred to as Planet 9, is speculated to be a large planet with a mass about 5 to 10 times that of Earth, but smaller than the ice giants Uranus and Neptune. Its orbit is believed to be highly elliptical, taking it far out into the solar system. It could take 10,000 to 20,000 years for it to complete a full orbit around the Sun. The gravitational pull from Planet 9 could explain the strange orbits of certain distant objects, leading to further investigation into its existence. No direct evidence of Planet 9 has been found yet, but its presence remains one of the most captivating possibilities in modern astronomy. Some researchers have speculated that Planet 9 might not be a planet at all, but rather a primordial black hole. This idea stems from the fact that the gravitational effects seen in the outer solar system could be consistent with either a planet or a smaller, denser object like a black hole. Primordial black holes are hypothetical black holes that could have formed in the very early universe, not from the collapse of stars, but from density variations in the first few moments after the Big Bang, existing even before stars or galaxies. These black holes would have a wide range of possible sizes, from extremely tiny to relatively large. The smallest ones would have evaporated by now throughout the universe, leaving only larger ones possibly detectable today. But even the larger ones are relatively small compared to black holes from other categories. The hypothesis relies on indirect evidence. The unusual clustering and alignment of the orbits of small icy objects in Kuiper Belt, a region of the solar system passing the planet Neptune, could be caused by the gravitational pull of an unseen compact object. In this case, a primordial black hole could cause these effects in the same way as a planet, but it would be very hard to observe such an object directly, because black holes don't emit light. However, astronomers are looking for other potential signs of its existence, like gravitational lensing, where the black hole could bend light from background stars, or its effects on nearby objects by detecting gravitational waves. Humans have evolved to navigate a world where threats are often visible, where danger has a form that can be understood or confronted. But a black hole is observationally a cosmic void, a destructive force that can't be touched or seen, a silent predator lurking in the vastness of space. If such a black hole were discovered in our solar system, the very idea of a small, invisible, and extremely dangerous black hole in our cosmic backyard, showcasing its gravitational powers, could easily trigger cosmophobia. The fear of something so elusive, hard to pin down, and so fundamentally bizarre is unsettling. The thought that something could be drifting unnoticed in the far reaches of our solar system. Even though a small primordial black hole wouldn't pose an immediate existential threat to Earth, it could be tugging on objects like asteroids or comets, poking them toward the inner solar system or even toward Earth itself. The thought of this black hole's influence, unnoticeable but important, could stoke fears of a cosmic catastrophe. What if the black hole had been causing unknown anomalies in planetary orbits that might lead to a larger disturbance in the distant future? Even though these scenarios might be unlikely, the very idea that something could exist totally beyond our control, an entity that exists far beyond the realm of our experience, yet could have unknowable effects on the very fabric of our solar system, is simply terrifying. Ultimately, black holes symbolize a cosmic threshold, a do-not-cross line set by nature. Their interiors are universe's way of saying that not everything can or should be understood. A humbling reminder of the limits of human understanding in the grand scheme of the cosmos. A black hole's interior is the very definition of the unknown, a region in which even the most advanced theories of physics can't predict what happens. The theoretical process of being swollen by a black hole challenges our sense of space, time, and existence, amplifying the fear of what lies beyond the reach of human experience. The fear of falling into a black hole and being torn apart is about not only the physical destruction of the body, but also the breakdown of our understanding of the universe. Our helplessness in the face of forces far beyond our comprehension, isolation, and loss of control. The very concept of spaghettification, where objects are stretched and compressed by gravitational forces as they approach the event horizon of a black hole, is a vivid and uncomfortable image that highlights the terrifying powers of these objects. Black holes represent the ultimate extremes: immense gravitational forces, unimaginable densities, and environments where reality itself is distorted. As black holes orbit and eventually merge, they create an extremely violent environment, pushing the boundaries of our understanding of the forces that govern the universe. The exact conditions required for a black hole merger are incredibly rare. However, when they do happen, the sheer power released is so overwhelming. They can't be predicted nor prevented. They're so rare that they feel like anomalies. The fact that such extreme and destructive events happen across vast stretches of space-time makes them feel alien and hard to grasp. The universe is a place where on unfathomable timescales, disastrous events of unimaginable energy, like black hole merging, can happen seemingly at random. Since information can't escape from within the event horizon, black holes act as perfect cosmic sensors, covering whatever happens inside from the rest of the universe. This notion of censorship also ties to philosophical and existential fact that some truths remain permanently out of reach. Black holes are embodiment of the fear of things that are so large, so powerful, and so beyond human control that they could become a source of deep anxiety. These fears might not be rational, but they are grounded in humanity's instinctive need to control its environment and understand its place in the universe.